let us continue our lecture devoted to description of characteristic functionals of probability distributions in the Hilbert infinitely dimensional Hilbert space. So, what is our situation? We have space H, which is a real separate Hilbert space. And we have the functional, which is defined on H, and take values in the set of complex numbers and satisfy some conditions. The first one, phi of 0 is equal to 1, phi of minus h is equal to phi of h complex conjugate. Second one, phi is non-negative definite. Non-negative definite. And third one, phi is continuous. We know that in case when the dimension of our space H is less than infinity, so when it is we can say usual finite dimensional Euclid space, then conditions 1 to 3 are enough for existence of probability distribution mu on H such that our functional phi of H is equal to integral with respect to H exponent I H U mu d. But we already have seen that such conditions are not enough in infinite dimensional case. And we already formulated the additional condition which was related to the family of nuclear operators on our Hilbert space. So when dimension H is equal to infinity, very different classes of operators arise. In contrast with finite dimensional case, we began to distinguish between compact operators and just bounded operators, between Hilbert-Schmidt operators and compact operators, between nuclear operators and Hilbert-Schmidt operators, for example. So we just produced the following definitions. Suppose that S is continuous operator of H, such that S with star is equal to S, such that S is non-negative in the sense of self-adjoint operators, and such that for some orthonormal basis K, which is orthonormal basis, we have the following relation. That the sum from K equal 1 to infinity, S EK is less than. This quantity is called trace of S, and it can be checked that it does not depend on the choice of orthonormal basis. If this condition holds, then S called nuclear operator, S is nuclear, operator. And we already have seen that that such operators naturally arise when we consider characteristic function of Gaussian distributions in vector space. So we already know that if we have a Gaussian measure in our Hilbert space, we have a Gaussian measure in our Hilbert space, then its characteristic functions have a special form, which are very familiar to us because it's exactly the same as in finite dimensional case. This is exponent here is the scalar product with the mean, and minus 1/2 of quadratic form of covariance. But now we know that S is nuclear. S must be nuclear. And this causes us to think maybe the continuity of the characteristic functional must hold in a weaker topology than usual topology related to the distance, original distance in the Euclid space, in Hilbert space. And it is true. So we formulated such Minlos-Sazonov theorem, let me recall. Let me recall that to conditions 1, 3, we must add the following condition 4, that for every epsilon which is greater than 0, there exists such S nuclear and S is non-negative, Z it follows from inequality SHH less than 1. It can be taken just 1 because we can multiply S on any positive number. It follows that distance to 1 of our functional is less than epsilon. So one can produce topology generated by such sets. Sometimes it is called nuclear topology, and in Banach space there are some analog of this nuclear topology, call it Maki topology, but now we consider just Hilbert case. And it occurs that this condition is necessary and sufficient for function to be characteristic functional of some probability distribution. Last time we proved that it is certainly necessary. So if we have arbitrary, not Gaussian, but arbitrary probability distribution on our infinite dimensional Hilbert space, then its characteristic functional is continuous in this nuclear topology. Now we are going to prove the sufficiency. And to do this, we discussed the Ulam theorem, just repeating the idea that probability distribution in infinite dimensional space must be concentrated on some special substance. We already have seen the variant which is called Ulam theorem. That for mu probability measure on our Hilbert space H, we have the formula for any epsilon which is greater than 0. There exists k epsilon which is compact, in H, such that mu of k epsilon is greater than 1 minus. We discussed a lot of this property, and from this theorem we know that any probability distribution in our Hilbert space is concentrated on the counted union of compact sets. But compact sets are rather difficult to discuss because we already have seen some examples. So for example, in C01, they are described using Ascoli-Arcelor theorem. In our Hilbert space, they are described by the property that the series which defines the norm of the elements converge uniformly on this set. And this counts us, this leads us to a much more appropriate in our main discussion condition for description of measures in our Hilbert space. More precisely, the last sentence which we made in the previous lecture was about the following property. We proved just using Ulam theorem that if mu still is probability distribution and we take any positive epsilon, then there exists the space subspace A of our space H such that it is finite dimensional. And we know that probability that distance rho of u to A is greater than epsilon is less than epsilon. Here I use this notation, but it is well known notation, and I use it like infimum. In Hilbert space, we can say here minima infimum of the distance u minus h, when h belongs to our space subspace. So now it is just difference between u and its orthogonal projection onto the space A, subspace A. So if we are trying to make some picture, it looks like that we can consider our Hilbert space H, because of we live in three-dimensional space, and this is our H, and then we can find such finite dimensional subspace, and then our measure is almost concentrated in small corridor, near this L, and this corridor has size epsilon in both sides. Yeah. So it occurs that such property is much more appropriate for discussing in sense of finite dimensional distribution. And let me show you why. First of all, we have to note that this notion to be flat concentrated, we can move to our family of finite dimensional distribution. So we don't need actually a measure in Hilbert space. It is just enough to have a family of finite dimensional distributions, and we can say, okay, this family is flat concentrated. So let us reformulate this property to be flat concentrated on the case when we have a family of finite dimensional distributions. Let me record what is a finite dimensional distributions. So if we have measure u in our Hilbert space, and we have just some h1, hn, which belong to our space H, then we can consider a linear span of these elements, and consider a projection of mu on this linear span. So we just discuss the following object: linear span of h1, hn, and we organize the projections. Projection of measure mu h1, hn on this linear span using these vectors. It is important. Using these vectors because we can generate the same linear span using another vectors. So we can define this one, and it is defined for all sets here, such that defined from the set of delta, where delta is an element of Pn. In such a way, this is a mu from such u that the vector h1 u hn u belong to delta. This is a measure. This is a measure Rn, or one can move it to this space, and this measure can be naturally considered in subspace A, this linear span H1, Hn. So one can say that from one side, this measure is defined on Rn, but from other side, it is placed here in our linear span. So for measure mu, we have a set of finite dimensional distributions. We have a set of mu, H1, Hn. And we discussed that this set is not arbitrary. They are consistent in sense of permutations, projections, and so on. So we have such a correspondence, but we already have seen that there are no backward correspondence. There are no backward correspondence. This means that one can have consistent family of finite distribution in our Hilbert space, but we cannot recover probability measure on our Hilbert space H. We considered very simple but important example when mu H1 Hn are corresponding to the standard Gaussian distribution corresponding finite dimensional space. But there are no standard Gaussian distribution in our infinite dimensional Hilbert space H. And we already know the reason. Its covariance matrix must be nuclear. So now we have just such correspondence, but let us think about the property of flat concentration. It occurs that it can be easily reformulated in this case on the language of finite dimensional distribution. So we will say that this consistent family of finite dimensional distributions mu H1 Hn is flat concentrated. For any epsilons which is greater than 0, there exists such a finite dimensional space, subspace A of H. That for any mu H1 Hn such that linear span of H1 Hn contains L, we have the same property. So mu H1 Hn from such U in our linear span that rho U add is greater than epsilon is less than epsilon. So you see the definition is almost the same. But instead of the measure mu, I just use this mu h1 hn under the condition that its linear span contains this subset A, which is corresponding to our positive number epsilon. So we reformulate the property to be flat concentrated on the language of our finite dimensional distributions, and it is easy to see that if we have family generated by probability measure, if we have family finite dimensional distributions which is generated by some probability measure, then this family is flat concentrated. Then mu h1 hn is flat concentrated. So we have such a statement, but it occurs that it works in backward direction. And this is our first statement for today, that actually we have this one. So if we have a consistent family of finite dimensional distribution, which is flat concentrated, then it is corresponding to some probability distribution in our Hilbert space. Let us do this like a sequence and prove it. Suppose that mu is flat concentrated, then there exists probability measure corresponding to this family. Okay. Let us prove this theorem. In order to prove it, I will say the following. It is very helpful from time to time stop to discuss probability distributions in Hilbert space and begin to discuss random elements in Hilbert space. So we have, let us know that we have such a one-to-one correspondence if it is say in such way. So if psi is a random element, in H, then we can consider we can put it in the correspondence is distribution mu, which is just image of initial measure under the variables. So when we want to say that there exists some mu with desired properties, it is enough to get the random element in our Hilbert space with some desired. Let us use this approach in our case. We already have the family of finite dimensional distributions. H. What does it mean? It means that for any H1, Hn, I can consider the random element, let's denote by xi H1, xi sigma n, such that mu H1, Hn is distribution. This is probability measures. Nothing. There are no any surprise. So now let us try to view such a sequence of random elements related to our finite dimensional distributions in such a way that they will converge to some random element, and this limiting element will have the desired distribution mu. Okay, let's do. Here we use property of flat concentration. I will choose a special values subscription. So I will suppose that I have a sequence of such subsets that they are increase. That they are finite dimensional. And that we have this property of that concentration in such a form for all H1, Hn, such that the linear span of H1, Hn contains Ln. We have the mu H1, Hm that we are far enough from the Ln. Okay, it's less than 1. So, due to the flat concentration property, one can choose such a sequence. The subspaces are chosen subsequently, and the next one is built using such using the condition of flat concentration and bigger than the previous one. Of course, if we take the largest subspace, then we will keep the inequality. Okay, then let us construct our sequence of random elements. I will fix the subspaces N and consider the sequence of measures mu and n And let us suppose that here we take orthonormal basis, and moreover that this basis is common for all sequence. So what I mean that if we have orthonormal basis, okay, one can build such one orthonormal basis. That if we just put here indices, this is natural numbers, then for example this first are corresponding to L1, then this next are corresponding to L2, and so on. So our subspaces L are generated by some finite increasing number of elements of basis. Now let us consider the family of finite dimensional distributions like mu1, okay, sorry, mu e I1, e I m, and m is the greater. Okay, so let's consider this set, and you see that this set is indexed by natural numbers. So here we see well-known and familiar to us from the course of random process theory set of finite dimensional distribution related to the natural parameter, and then we understand that there exists a family. Let me denote it by alpha I. This sequence is a sequence of random variables. With such finite dimensional distributions. Yeah. With such finite dimensional distributions. Moreover, now one can say that mu Ln is a distribution of, and here we put the sum. Let me denote it by psi n. It is sum from e equal 1 to sum an of alpha e. So we just built the sequence of random elements psi n in our input space. What is remain is to prove that the sequence converges in Hilbert space. But it follows from the fact that now it occurs to be fundamental. It occurs to be Cauchy sequence. Really, if we took the norm of psi n plus 1 minus psi n and consider the probability that this norm is greater than 1 over 2n, then it is exactly mu of Ln plus 1 from such u that rho u Ln is greater than 1 over n. Consequently, it is less than 1/2. Okay. Now it follows easy from the Brinkentelli lemma that this series converge. It exactly means that psi n is Cauchy sequence. It is sufficient for psi n to be a Cauchy sequence, and consequently there exists a limit. Psi n tends to some psi when ends to infinity everything. And I left as an exercise for you just to check the finite dimensional distribution of psi coincide with our family mu h1 hn, which was given. So the theorem is proved. In view of this theorem, when we are checking the Sazonov theorem, it's enough to check the property of that concentration. For our for what? For what? This is another step which we have to do. You see, if we have the functional phi, which is with properties 1, 4, then evidently a restriction of phi on any finite dimensional subspace satisfy usual Buchner-Finchen theorem. Yes. So because it is equal to 1 at point 0, it is symmetric in the sense of complex conjugate. It is non-negative, definite, and it is continuous, of course. Yeah. We have a restriction of this finite dimensional subspace. Due to this, one can say that now phi restricted on A is correspond to some probability measure. So it is equal to mu L Fourier transform. And now one can check that this family mu L, where dimension L is less than infinite, is consistent. By the way, it is a good exercise how to check this. What is the reformulation of consistency condition in the sense of characteristic functionals? Of course, it is easy. We just if we have coordinates, for example, we have finite dimensional case, and just put the last coordinates to be equal to 0, we must have the characteristic functional of the measure which is concentrated on corresponding subspace. So it's easy to check that it is consistent. And now what is remain to check? That this family is flat concentrated. I will not check this in all complexity. The reason is the following. It is rather technical, and we already have all ideas. So I will check it in the following. Let us consider the positive number epsilon, and let us prove. Let us check that we can control mu L n plus 1. Okay, maybe n prime from such u that rho u is greater than epsilon. In case when A is subspace of A prime, but dimension of the orthogonal difference A prime minus A is equal to 1. I just will control this. Of course, this is not all proof, but before we see how we can organize Cauchy sequence. So more or less it's enough. How one can proceed in this case? Let us, so what we need. I will prove that there exists such A, that if we have just one-dimensional extension of this L, then we have such estimation. Yeah? By the way, this L prime is not uniquely determinant because it is infinite dimensional space. So we just fix A, and it's better to imagine it is a line. So we just can add this just one orthogonal vector, but in any direction, and in infinitely many directions, actually now. So I will just prove such property. There exists such L for any x. How to prove it? How to prove it? Now let's use this continuity in nuclear topology condition. So for this epsilon greater than 0, one can find S negative nuclear that from the condition SHH is less than 1, we have that 1 minus phi of h is less than h. So what we now going to do? S is self-adjoint, non-negative, and nuclear. So it has eigenbases with eigenvalues. So suppose that En is a eigenbasis. Of course, orthogonal is orthogonal, and I will take the range of any vector from this basis equal to 1. S and lambda n corresponding eigenvalues. S En lambda n. Then what we know the trace of S, which is equal to sum from n equal 1 to 50 of lambda n's is less than 50. From this one can conclude that there exists such capital that the remaining sum from n equal n capital plus 1 empty n is less than epsilon. Now let us consider as a candidate for our subspace A this linear span of the first n capital elements of the basis. Then see what happens if you just add some to organize a prime. Yeah? Now take some h, which is orthogonal to L. I am trying to organize L prime, and we discussed that the dimension of L prime is just 1 plus dimension of L. So to organize L prime, we have to add some vector, which is orthogonal to L, and I will suppose that the norm of H is equal just 1. Then it occurs, then one can define L prime as L plus T H. T is from R. This is just one-dimensional subspace, which is related to R vector H. And then one can see the following. Suppose we have the mu of such u that rho u a u prime u rho u a is, and we want to estimate. I will not do this in all complexity because of technical details which I said to you. I will just discuss the following case. I will consider the 1 minus phi of th. It is not enough to estimate this thing, because this value is related to measure concentrated on the one-dimensional subspace generated by H. When we consider general situation, so this is our L, this is our L prime, and here is the vector H, and we just have to consider all conditional distributions related to such picture, and then consider any conditional distribution here, and prove that for these conditional distributions, for every, we can estimate the tail when we get far from our subspace A. But I will not do. I will just consider estimation of this kind because the work is more or less the same, but it's rather technical. And here we have already the estimation. If you remember the course of probability, then it was proved in those course that if one can estimate the following integral from minus c to c modulo of this one dt, then it means that we can estimate for our distribution mu h. Again, I emphasize it is not all proof, it is just ideas, it is not conditional distribution, but the work is the same. We can, this guy is less or equal than mu h of such u that mu h modulo is greater than some r. Yeah, there are some relations between these constants, but the idea is clear. We just want to estimate how close is our characteristic function to 1 in some neighborhood of 0. And when we get the estimation for this one, we automatically get the estimation for the tails of the distribution. This is the idea. But now we have it, because what we have here, it is less or equal than what? Than epsilon, yeah? Because when c, I put here 1 and here minus 1, then I will get here epsilon. Yeah, why? Because we already discussed it, that we took our operator S in such a way that now, because of H is orthogonal to En and has north equal to 1, then is HH now is less than what? Here we have the following. Okay, let's check. It's equal to sum from n equal n plus 1 to infinity lambda n, and here is coordinates hn in square. Yeah. Okay. So we just took this n from the condition that the series is converged, and that the remaining term is less than 1, but maybe it is okay, maybe it is not enough for us, because I want that this one is less than epsilon. Then let us slightly back and choose our n more precisely. Choose our n more precisely. Okay. For example, one can suppose that lambda n are equations, and say that let n is capital such that lambda n is lambda n capital is less than epsilon. Because h has no equal to 1. But of course, this is only idea. we have to be careful because of we don't consider conditional distribution. We just add one dimension, but these steps are main and give you a flavor what is called when we prove sufficiency in Verloos-Sazonov theorem. So we will say that we are finishing discussing the ideas of the proof in Verloos-Sazonov theorem, and from now we know that the characteristic functional of probability measure in infinitely dimensional Hilbert space must to be continuous in the nuclear topology. And this is necessary and sufficient condition for non-negative symmetric special self function to be characteristic functional on some probability distribution. During the proof, we discussed a very useful notion of flat concentration for one probability measure from the family of finite dimensional distributions. And we will use this property in the next lecture when we will discuss the weak convergence of probability measures in our Hilbert space. Because what we did, we are going step by step in a way which we already passed through in finite dimensional case. In course of probability, we start from studying of characteristic functions. And what was the next step? Next step was characterization of the weak convergence in terms of characteristic functions. So maybe the same was OK in infinitely dimensional case. What we did already, we already described all characteristic functions. So next natural step is to discuss weak convergence of probability distributions in the infinitely dimensional space and to think how it can be expressed in terms of characteristic functions. That's all for today. Thank you for the attention. Maybe somebody has questions or comments, please. Okay. If not, then thank you again and